Welcome to SSR Pharma Media, your trusted source for pharma knowledge. Pharmaceutical Inorganic Chemistry MCQ series, your exam power boost. Today we are going to discuss about isotonicity. Prepare, practice, succeed. So in that isotonicity, we are going to see what is isotonicity and applications in IV fluids and ophthalmic solutions. Define isotonicity. So isotonic solution are those that have the same osmotic pressure as that of body fluid like plasma, blood, tears. So no yet movement of water occurs across the cell membranes. So physiological osmotic pressure of the body fluid is 7.4 atmosphere ATM. So equivalent to 0.9 percentage weight in volume sodium chloride is equivalent to this atmospheric pressures. That means osmotic pressure. And types of isotonicity. So types of isotonicities are the solution which are not having the same osmotic pressures are called as paratonic. While comparing a solution with one of known osmotic pressure, so those exert a greater pressure are called hypertonic, and those with lower pressure called hypotonic. So the osmotic pressures, isotonic solutions, and hypertonic and hypotonics. So there are three types of solution: isotonic solution, hypotonic solution, and hypertonic solution. Isotonic solution means no change in cell size. Example, 0.9% of sodium chloride is called as isotonic solution. Hypotonic means, so in hypotonic conditions the cell swell and it burst. That means it occurs hemolysis. Due to the bursting of cells occurs hemolysis. So example, distilled water, it's called hypotonic. Distilled water without ions, it's considered as a hypotonic solution. Hypertonic means, so it's in the hypertonic solution cells get shrink and crenation takes place. The shrinkage of cells takes place. So example, strong salines. So that means, so more than 9% of sodium chlorides containing solutions are called as strong saline. So these are all the three types of isotonic solutions and effects on the cells examples. So applications in IV fluids and ophthalmic solutions. So why IV fluid must be isotonic? Because it directly enters the bloodstream, and when it is when the solutions are not isotonics, so there are chances of to being as a hypotonic or hypertonic. So hypotonic solution means when it's entering into the bloodstream, it leads RBC lysis. That means RBC cells are burst. Breakdown of RBC cells takes place. Suppose it's a hypertonic, so in that case, RBC cells are shrinkage takes place. So in these both conditions, this RBC red blood cells will not properly transport the other minerals and oxygens. So that's why the solution should be isotonic. So in isotonic, there is no RBC lysis and there is no RBC shrinkage. So osmotic common isotonic IV fluids are normal saline, ringer solution, ringer lactate, and 5% of dextrose. So these are all the composition of this fluids, and it is used for mainly so fluid replacement, electrolyte balance, acidosis corrections, and energy sources. So why isotonicity in ophthalmic solutions? So ideal isotonicity means ophthalmic solution should be isotonic with lacrimal fluid. So equivalent of 0.9% of sodium chloride is called considered as isotonic solution. So that's equal to lacrimal fluid. Acceptance range of sodium chloride equivalent method when the preparation of ophthalmic solutions. So we have to add 0.6% to 2% of sodium chloride equivalent. in order to make the solution isotonic, and slight deviations tolerated due to tear dilutions. Why isotonicity is important? It prevents the irritations and pain, avoid reflex tearing, and improve patient complaints. So finally, the importance of isotonicities are prevents hemolysis of RBS, RBC, avoid pain and tissue damage, and maintains regular integrity, and essential of for parenteral and ophthalmic preparations. So we'll move into the questions. An isotonic solution is best defined as one which, so option B, has the same osmotic pressures as body fluid. Which of the following solutions will have hemolysis of red blood cells? So option C, distilled water. So because distilled water is the hypotonic solution. So in hypotonic solution, cells get burst, RBC get burst or breakdown, swell and hemolysis takes place. Physiological osmotic pressure of blood plasma is approximately equivalent to option B, 0.9% weight in volume, sodium chloride. Which of the following is an important advantage of isotonic formulations? So option C, prevent hemolysis of RBC. So tonicity. So in this we are going to see the adjusting isotonicity. So calculations for solution isosmotic or isotonic with blood and tears. So the methods of adjusting isotonicities, there are four methods mainly. First method, methods based on freezing point data, depression data. So it is also called as cryoscopic method. Method 2, method based on the molecular concentrations, is a one-half method. And method 3, graphic method based on vapor pressures and freezing point depression method. Method 4, method based on sodium chloride equivalent method. So first method is method based on freezing point data. It's also called as cryoscopic method. So in this method, in this cryoscopic method is an analytical technique. It's used to determine the molecular weight of solute by measuring the freezing depression in the freezing point of solvents when the solute is dissolved in it. So the main thing is depression in the freezing point. Method based on the freezing point data is a cryoscopic method. In this method, adjust isotonicity by comparing freezing point depression. So delta T half TF of the solution with that of blood or tear. So the blood or tear freezing point depression is minus 0.52 degrees Celsius. So colligative property. So freezing point depression is the methods of the colligative, one of the methods of the colligative properties. So colligative properties are the physical properties of solution that depends only on the number of dissolved particles. So not on their nature, only the number of dissolved particles. So these properties are independent of the chemical identity of the solute. So freezing point of the body fluid is in blood, plasma and tears freeze at minus 0.52 degrees Celsius. This indicates that dissolved substance in this fluid lower the freezing point by 0.52 degrees Celsius compared to pure water. So any solution freezing at minus 0.52 degrees Celsius is said to be isoosmotic with blood, plasma and tears. Next method based on the freezing point data are cryoscopic method. So for this explanation, every solute lowers the freezing point of water. Blood and tear fluids shows freezing point depression of minus 0.52 degrees Celsius. The solution is isotonic when its delta TF equals to 0.52 degree Celsius. If delta TF of drug solution is lower, an adjusting agent of sodium chloride is added. So importance of this method is accurate and scientific method, useful when freezing point data of drug is known, widely applied in ophthalmic and injectable preparations. So in this method formula, freezing point data method formula, percentage weight in volume adjusting substance needed. So it's a formula 0.0.52 minus A divided by B. So this is the formula. So B should come here. So in that A means freezing point of an adjusting solution. B is a freezing point of 1% weight in volume solution of the adjusting substance. So according to that, we will take the one example. So find out the concentration of sodium chloride. To adjusting the isotonicity, we will use sodium chloride. So sodium chloride required to make 1% solution of boric acid isoosmotic with blood plasma. So freezing point of 1% weight in volume of boric acid is minus 0.288 degrees Celsius. So at the same time 1% solution of sodium chloride freezing point depression minus 0.576 degree Celsius. So now we are applying this formula. We will get the freeze how much weight of the sodium chloride to be taken to make the solution isotonic. So 0. We are substituting in this formula. So 0.52 minus 0.288 divided by B means is the sodium chloride. So 0.75, so 0.576. So finally we will get the answer 0.402% weight in volume. So we'll move into the question. Blood plasma and tears are considered isotonic with solution that freeze at minus 0.52 degree Celsius. So a 1% weight in volume drug solution shows freezing point depression 0.30 degree Celsius. To make isotonic using cryoscopic method, the formula should be, so option C, adjusted by adding sodium chloride. So when 1% of solution of boric acid is to be made isotonic with blood plasma, given that freezing point, here 1% of boric acid 0.8, 1% of sodium chloride minus 0.576 degrees Celsius. So we are already we have seen the calculation. So the answer is option B. So minus 402% weight in volume. So when we are substituting this formula, A means is a boric acid freezing point depression 0.288 and for 0.52 minus 0.288 divided by B means sodium chloride. So 0.576. So finally the answer is 0.402% weight in volume. So the same questions. So 1.5% solution of cocaine hydrochloride made to be isoosmotic with blood plasma and given the freezing point and what concentration of sodium chloride is required. So 1% of sodium chloride freezing point depressions already we know minus 0.576 degrees Celsius. So cocaine hydrochloride they have already given minus 0.09 degrees Celsius. So when we should apply on the formula of 0.52 minus A divided by B. So the answer is option C. So you are applying this formula. So 1.5%. 1 means will simply the previous we added only 1 into 0.09222. So we'll get 0.288. So but here 1.5%. So minus 0.52 into freezing point depressions 0.09 into 1.5 divided by sodium chloride freezing point depressions 0.576. So the answer is 0.668. So in this question, previous question, these questions are same only different. So they have given only the 1% of the cocaine hydrochloride is freezing point, this one. So here the questions they have given 1.5%. So that's why 1.5 into 0.09 we have to multiply. So this formula instead of for A. So second method is methods based on the molecular concentration, 1/2 method. So in this method, molecular concentration means the number of units, that's molecules or ions or both present in a solution. So a solution containing 1 gram molecule of a non-ionizing solute in 22.4 liters at normal temperature and pressure and has an osmotic pressure of 1 atmosphere. So, a solution containing 1 gram molecule in 1 liter will have an osmotic pressure, so 22.4 atmosphere. So, the osmotic pressure of blood plasma and lacrimal secretion is approximately 6.7 atmosphere. So, the molarity of fluid 6.7 divided by 22.4 is equal to 0.3 m molarity approximately. So method based on the molecular concentration. So this is the approximate calculations. So here it's a molar, m is a molarity. The final formula for this 1/2 method is W is equal to 0.3 m divided by n. So this is the final formula. Remaining you read it, what is m, what is W and all. So here n is equal to number of ion produced from each molecules of the solute, assuming that dissociation is complete. The osmotic pressure of blood plasma is approximately 6.7 atmosphere. The molarity of blood plasma is therefore closest to, so option C, 0.30 m molarity. What is the correct formula to calculate the concentration of an ionizing solute required to make an isoosmotic solution with blood plasma? So option C, 0.3 m divided by n. Find out the proportion of dextrose needed to form solution isoosmotic with blood. So here dextrose molecular weight they have given. Dextrose is a non-ionizing substance. So according to that, answer is option A, 5.4 gram per 100 ml. So in this 1/2 method, 0.3 into 180. 180 is the molecular weight. So it gives approximately 5.4 gram per 100 ml. This 54 is the answer, 54 per liter. So per liter 54 means per 100 ml. 1 liter is containing 10 ml. 10 ml. That means 1 liter is equal to 1 liter is equal to 1000 ml. So for 100 ml we need to calculate. So 5.4 gram. Find out the concentration of sodium chloride required to produce a solution isoosmotic with blood plasma. So option D, both A and C. So this is the formula, 0.3 into 5, 58.5 divided by 2. So 8.8 gram per liter or 0.88 gram per 100 ml. So both is correct. 80 per liter also it's correct, and A and C per 100 ml also it's correct. While adjusting a paratonic solution to isotonicity using sodium chloride or dextrose, the first step in calculation is to, so option C, calculate the effective molar concentration of drug. So next, third method, graphic method based on vapor pressures and freezing point depression. So in this graphical method where isotonicity is determined by plotting concentration versus vapor pressure lowering or freezing point depression. So in vapor pressure lowering is proportional to solute concentration. Freezing point depression is directly related to vapor pressure change, and graphs helps determine isotonic concentration visually. So it is very important and useful in research and reference studies and helpful when exact freezing point data is unavailable. So less common in routine pharmacy calculations. In graphic method for adjusting of isotonicity based on freezing point depression, tonicity of a medicament is determined by, so option C, plotting percentage concentration against freezing point depression. So next, fourth method based on the sodium chloride equivalent method. So E value method. So E value is the amount in gram of sodium chloride osmotically equivalent to 1 gram of drug. It is based on factor called sodium chloride equivalent method, which can be used to convert a specified concentration of medicament to the concentration of sodium chloride, which will produce the same osmotic effect. Sodium chloride equivalent can be calculated from the following formula. Sodium chloride equivalent method is equal to freezing point depression by a solute divided by freezing point depression produced by sodium chloride. So the percentage of sodium chloride for adjustment to isotonicity is, so minus 0.9 minus percentage strength of medicament solution into sodium chloride equivalent of medicament. So here 0. The short formula 0.9 in minus C into E. C means percentage strength of the medicament. E means sodium chloride equivalent. Sodium chloride equivalent of your medicament is defined as, so option B, the amount of sodium chloride having the same osmotic effect as 1 gram of the medicament. The percentage of sodium chloride required to adjust medicament solution to isotonicity is calculated using the formula. So option C, sodium chloride, percentage of sodium chloride is equal to 0.9 minus E into X. So C into E. C means percentage strength of medicament. E means sodium chloride equivalent. Calculate the percentage of sodium chloride required to make 1% solution of procaine hydrochloride isoosmotic with blood. So sodium chloride 1% of procaine hydrochloride 0.21. The strength of procaine hydrochloride 1%. So the formula is 0.9 minus C into E. So where C is percentage of the medicament, percentage 1%, and E is the sodium chloride value. So sodium chloride equivalent. So 1 into 0. So 1 is the C means is the percentage of the medicament. 1 into 0.2, it is sodium chloride equivalent method value 0.21. So finally 0.9 minus 0.21 is equal to 6.69. So the answer is option A. Calculate the percentage of anhydrous dextrose required to make 1% of solution of epidine hydrochloride isoosmotic with body fluid. So here also same like that. So this formula. So here C is the percentage of medicament. Percentage of medicament is the 1%, and sodium chloride equivalent method is 0.3. So here 1.9 minus 0.3. So we'll get 0.6. So this 0.6 in the percentage equivalent to anhydrous, 0.6 divided by dextrose 0 freezing point of the dextrose is 0.18 percentage. So 0.6 divided by 0.18, it gives 0.3, 3.3. So the answer option B is the correct answer. So next is so these are all the important drugs, and it's a isotonic with the body fluid, the weight in volume. So ammonium chloride means 0.8 gram in weight in volume is make the solutions isotonics. The same time, sodium chloride means 0.9 grams of sodium chloride. Boric acid means 1.9 gram of sodic acid. Boric acid in 100 ml, it gives isotonic. Ephedryl hydrochloride, 3.2 gram of ephedryl hydrochloride. Solution is isoosmotic with body fluid. Dextrose is 5.05. It's a very important. Repeatedly they are asking in the different uh, competitive exams. Adjustment to isotonicity and volume methods. So White-Vincent method and Proulx method. There are two methods. White-Vincent method, a volume method based on the fact that a given quantity of drug forms an isotonic solution when diluted to specific volume with water. So this is the formula. Volume is equal to 1 liter 1000 ml into W into E divided by 0.9. So its final formula will get it. V is equal to W into E into 111.1. So this is the abbreviation for this. V is the volume of volume to which drug is diluted with water to make isotonic solution. W is the weight of the drug. E is the sodium chloride equivalent of the drug, and 0.9 is the isotonicity of sodium chloride. And adjustment to isotonicity. So next, Sproul's method, a modified White-Vincent method, uses pre-calculated tables to determine isotonic volume directly. So in this procedure to determine the isotonicity from Proulx tables, find volume of isotonic solution produced by 1 gram of drug. So multiply this value by actual weight of the drug used. So prepare solution up to this volume with water. Adjust final volume with isotonic diluent if required. So no calculations required, fast and more convenient based on tabulated E values. The White-Vincent method for adjustment of isotonicity is based on, so option C, volume of isotonic solution produced by the drug. The Sproul method differs from the White-Vincent method because it, so C, use of table to directly obtain isotonic value. Calculate the percentage of sodium chloride necessary to make an injection containing 2% of procaine hydrochloride isoosmotic with body fluid. So answer, calculate and answer in the comment box. Thank you. So all of you join in our WhatsApp community. You will get hands-out material. Thank you. Like, subscribe and share.